Okay, this is a set of notes on geometric proof. Last time around, we used a geometric proof model to justify algebra problems, but now we're actually going to do this with geometric content. So remember that deductive reasoning is reasoning that uses accepted statements. So there are 4 different things that we can use as accepted statements in geometry. The first one is information that's given by the situation. So we just call it given information. And then usually in the reason blank of the 2 columns, we just put the word given in there to represent that that's what it is. The second thing is we use definitions. So definitions are things that we agree upon that what a word means. So like we've had a definition of an angle, a definition of a line segment, definition of a perpendicular bisector, things like that. Ultimately, definitions are things that are just commonly agreed upon. Usually they're pretty much consistent across the mathematical world. We'll run into a few here and there that are not, and we'll talk about why that is. So yeah, that's what it is. Remember though that we had 3 terms that are never defined: a point, a line, and a plane. Those are left as not defined, and there's some specific reasons for that geometry, but most of all it's because they're very difficult to define. We have things that are called postulates. When you use a postulate in algebra, you call it a property. Postulates are things that you cannot prove, but you don't need to because they're immediately available to your senses. So, like, it's something that's like you can understand and you can see its truth without having to actually give argumentation for. And the last one are what we call theorems that have previously been proven. Okay, so theorems are things that we've already proven. So they're theorems that have been proven. And this allows us to make a leap from one thought to another using a proof that we've done in the past. So once we've proven a theorem, we don't have to keep reproving it each time. We just state that theorem and we move on. So the ideal thing to do at this point would be to actually state a theorem that we can use for other things and then show how a proof for that theorem would work. So a pretty important theorem that we use in geometry is what we call the midpoint theorem. And the basic statement of this is that if I have a line segment, and let's call the line segment AB, and the point M is the midpoint, so it's the midpoint because AM is congruent to AB, then the theorem states that if M is midpoint of segment AB, then we get actually 2 conclusions here. We can say that AM is half of AB and MB is also 1/2 of AB. Okay, so this is what the theorem states, that the distance from A to M is half the distance of the whole, and the distance from M to B is also half the distance of the whole. So this is what we're going to prove, and we're going to do this in a formal way. So typically in a proof, there's a drawing provided, usually, and the drawing that's here is pretty logical. Create AB with M as the midpoint, and then we have certain given information. We are given that M is the midpoint of segment AB, which derives directly from corresponding the sketch in the proof to the hypothesis of the theorem. So the if part of the theorem was if M is the midpoint of AB, our segment AB, so our given is a direct statement of that hypothesis. The thing that we're trying to prove here is the conclusion of the theorem, the then part. So AM should be half of AB, and MB should be 1/2 of AB. So just like we did with algebraic proof, we're going to build a structure that has two columns here. And one is going to be a statements column, and the other one will be a reasons column. Okay, so most proofs start in the same place. They start with the if, the given portion here. So we're going to say that M is the midpoint of segment AB. And why do I know this? Because that's given information, and I can say that that's given to me. Okay, so because it's the midpoint, we know that it cuts the segment into two congruent parts. We then know that AM has to equal MB. This is what it means to be a midpoint. So that is the definition of a midpoint. Okay, so we actually used an accepted statement, which is the accepted definition for what a midpoint is, to break this into an equation. Okay, so but if I look where M is, I know that AM plus MB has to equal AB, because M is between A and B. So if I go from A to M and then from M to B, it has to be equal to the whole distance. That was because of what we call the segment addition postulate. So postulates are another form of accepted statements, and we're good with that. Okay, so if I take this earlier statement and I take out the MB below here and I put in an AM, I get that AM plus AM is AB, or another way of saying that is that 2 AMs equal AB. Alright, so I took out something, put in something else that's equal. That's using the substitution property. Okay, so that makes sense. That's using a property from algebra. And if I take the 2 and bring it over to the other side by division, I get that AM is 1/2 AB, which is one of the two things I'm trying to prove, which is awesome. So what do? I divided both sides by 2. That's the division property. All right, so that gets me one of the two things I want to prove. And then if you look, we know that AM back here is the same as MB. So I can take that AM out and I can put the MB in. Gives me 1/2 AB. That says MB is 1/2 of AB. That's the other thing I'm trying to prove, which is awesome. So that's what I do. I took out something, put in something that's equal. That's using the substitution property. Okay, so there you have it. That's just a pretty straightforward geometric proof. So typically we use two-column proofs to prove theorems in this course. This is an example of one. We're going to do a lot more of them as the year goes on. Remember that there's 4 types of statements that can be used when you're using deductive logic in a proof. You can use given information, like we did here. You can use definitions, like we did here. You can use postulates or properties, like we did here, here, and here, and here. And you can also use proven theorems. We didn't do that in this one, but hey, now you can use this theorem to prove other things, which is awesome. All right, so remember there's a set of notes to back this up, and we'll move on from there. Thank you.